Welcome back to part 3 on Intro to Trig Functions and Identities. Let's start looking at the Pythagorean identities. Most of you remember that the Pythagorean theorem is a squared plus b squared equals c squared, where c is the hypotenuse and a and b are the sides. The trigonometric functions are related to each other through several important equations called trigonometric identities. We've already seen the reciprocal identities. Now we'll look at Pythagorean identities. Using the Pythagorean theorem, simplify the following expression. You might not know what to do here when it says sine squared theta plus cosine squared theta equals blank. The basic idea here is to recognize that when you're looking at the x coordinates, that's like your cosine. And when you're looking at the y coordinates, that's like your sine. So if I were to use those rules, I would say y squared plus x squared equals r squared. But if it's a unit circle, what do we know is true about that? Well, we know that if it's a unit circle, the radius creates the coordinate point on the rotation. So xy is your terminal point, and the radius is equal to 1. So I know that x squared, because we like to write it in order from alphabetically the first to the last, so x squared plus y squared is equal to 1. So that means that sine of theta, and that's sine squared theta, plus cosine squared theta equals 1. And this is your first identity, and from that identity we can derive two others. This is the most important identity, and you must remember it. It's absolutely crucial. So let's go ahead and highlight that one. If there's any identity that you memorize from this handout, this is the one you should memorize. And I would take a minute to see if you can relate it to the unit circle yourself. I would take a blank sheet of paper and try and recreate this sketch that I have here with theta, the triangle, the right triangle in the first quadrant, the radius r, the terminal point xy, the x direction is, or the horizontal direction is x, the vertical direction is y. Just see if you can recreate this from memory. If I start with sine squared theta plus cosine squared theta equals 1, and I subtract sine squared theta from both sides, I get cosine squared theta is equal to 1 minus sine squared theta. And then if I wanted to just have cosine, not cosine squared, I take the square root of both sides. And I get cosine theta is equal to plus or minus the square root of 1 minus sine squared theta. So as you can see, you can manipulate the original statement to look very, very different. So the following are Pythagorean identities. We've talked about the sine squared theta plus cosine squared theta equals 1. And now we also can derive tan squared theta plus 1 equals secant squared theta, and 1 plus cotangent squared theta equals cosecant squared theta from this first one here. Before I show you how to do this, I'd like you to pause the video and see if you can derive this second and third identity from the first one. It can be done, so give it a try. Welcome back. We're going to start with sine squared theta plus cosine squared theta equals 1, and try to find tangent squared theta plus 1 equals secant squared theta. Or when you're trying to morph from one identity to something else, you can look at what your goal is. So I know that tangent of tangent squared theta is sine squared theta over cosine squared theta. And so if I have a sine squared theta in my first identity, then I'm going to divide that sine squared theta by something that will make a tangent squared theta. That means I need to divide by cosine squared theta on both sides. So I'll divide all the terms on the left of the equal sign by cosine squared theta, and on the right side by cosine squared theta. When I do that, I magically get tangent squared theta plus 1 equals secant squared theta. How convenient. So I just showed that I can derive tangent squared theta plus 1 equals secant squared theta simply by dividing the whole original identity by cosine squared theta. Let's see if I can do something similar with 1 plus cotangent squared theta equals cosecant squared theta. I happen to know that cotangent is cosine, and this is cotangent squared theta, so we'll keep with the pattern, cosine squared theta over sine squared theta, which is the reciprocal of tangent squared theta. Which means if I divide everything by sine squared theta, I'm probably going to get what I want. Again, starting out with sine squared theta plus cosine squared theta equals 1. Dividing everything by sine squared theta this time. Gives me 1 plus cotangent squared theta equals cosecant squared theta. Ta-da! It worked. And this shows that I can derive the second Pythagorean identity from my first Pythagorean identity and get the new one. 1 plus cotangent squared theta equals cosecant squared theta. In example 4, we're given if cotangent of alpha is equal to 3 over 2, and alpha is in quadrant 3, find the other trig functions. This is a little tricky, so let's go ahead and sketch a picture. First, I need to remember that cotangent of alpha is equivalent to cosine of alpha over sine of alpha, and that it's equal to 3 over 2. We also know that alpha is in the third quadrant. In this particular instance, we cannot assume that the radius is 1. But we can figure out what our other values will be based on the fact that cosine alpha equals 3 and sine alpha equals 2. If we were to sketch this, we'll have some sort of triangle in the third quadrant. And so I'm just going to expand this out. And we know that x is equal to 3, y is equal to 2. But we are in the third quadrant, so the point, the terminal point for this angle that's rotated through into the third quadrant is going to be the coordinate point -3, -2. In which case we can figure out what the radius will be. The radius is the square root of a squared plus b squared. We'll go ahead and say 3 squared plus 2 squared. That gives me r is equal to 9 plus 4, or the square root of 13. That allows me to write all the other trig functions. Sine of alpha is -2 over the square root of 13. And rationalizing, -2 root 13 all over 13. Cosine of alpha is equal to -3 over root 13, which is equal to rationalizing, gives me -3 root 13 over 13. Tangent of alpha is -2 over -3, which gives me 2/3. Now let's find cosecant. Cosecant is 1 over sine, so it's going to be root 13 over 2, and it's negative because I'm flipping sine alpha over. Secant of alpha is going to equal 1 over cosine, so negative root 13 over 3. I think it's important to note at this point that we are not finding angles. These are not radians. These are lengths. All of these are lengths. Length, 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 length. And I say that and I emphasize that because it's such a common error. So these are all lengths. It's important to keep track of the difference between an angle, which we don't know. We could find it. We'll find it later, but we have not been given an angle. We've just been given the ratio of the sides of the triangle in the third quadrant.